Hiya. So in the last few videos, we've been talking about like rotations in 3 dimensions, and it's probably a good idea now to actually see an example of what is happening and going from there. So we're gonna look at an orthonormal basis B, and from a previous example from I think maybe last week, we had that the following linear operator. So we have the following linear operator. And we know that it's linear. So the question is P an orientation preserving orthogonal operator? Right? So is this true? This is another way of saying, is P a rotation? If so, what is the angle of rotation? So can we actually figure out the angle of rotation or no? Because remember last time we were talking about it does it by sine, but we might not know if it went one direction or another. So let's see if we can figure out the angle of rotation if this is in fact a rotation. So first off, what we're going to look at is the matrix, right? So what we'll notice is the operator is swapping the first two basis elements. So EY and EX are swapped. So what this kind of gives us is a swapping here. And then we know that Z is sent to its negative. So we have a -1 for the Z. So if you look at this, the column vectors are precisely what we had before. So there's not a big thing. So this is the matrix of the linear operator. Now, can we check if it's orthogonal? It's not too hard to see. You just have to multiply by its transpose. So let's kind of do this on the side. So the transpose is actually the same thing. Nice and easy. So let us multiply. So I like to do this for multiplication, so I remember. So here we have 0, 1, 0. So the top left is going to be 1. Then we get 0 and 0. Then I get 0, 1, 0. And then I get 0, 0, and then -1 times -1 is 1. So I do get the identity, so it is orthogonal. Therefore, orthogonal. Okay, cool. So we have orthogonality. Now, if we look at the determinant, this is actually just going to be +1. So you can kind of see if I look at these, the ones I have, right? Then I have 1 times -1. But here I need to do this minus sign. So I have a minus of all this. So we have 1 for the determinant of the linear operator. Remember the linear operator, the determinant doesn't care what the linear operator is. So it does preserve orientation. So it is, therefore, it is an orientation preserving determinant of P is greater than 0. Orthogonal MTM is equal to the identity linear operator. Okay, and therefore, oops, you can't see. And therefore, this is a rotation. Therefore, P is a rotation. Rotation by Euler's rotation theorem. Now you might be looking at this and going, well, wait a second. This doesn't look like any rotation, like the rotations we defined before. Because remember how we defined it? We kind of said, oh, we need this cosine of phi, cosine of phi, sine of phi, sine of phi. And you're like, yo. You went from something super easy, here's a nice matrix, blah, 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 to something much more complicated. There's no 1 on the diagonal. Like, what the hell? What is happening? Now, the thing is, remember that these matrices are dependent on the basis that's chosen. And so one of the things to notice is recall that sometimes you're going to get a rotation that doesn't look like the standard rotation matrix. So it's something to note. This is why Euler's rotation theorem is very strong, because we don't have to have something in this format. We just multiply by the transpose. We look at the determinant. And these two things will tell us if it is or is not a rotation. Okay. So then what we have to now calculate, okay, what is the axis of rotation and what is the amount that this rotated by? So one thing to note by Euler's rotation theorem is that we said the eigenvector whose eigenvalue is 1, this is precisely the vector that is the axis of rotation. Okay, so what is the eigenvector? So this we actually already calculated in a previous video. This is, so in example 1.56, let me see what week this was from. I think this was week 2, actually. I thought it was this week, but maybe it was week 2. Yeah, week 2. So in week 2, we looked at this. It's on page 21, if that helps. And we basically showed that the eigenvector, I can't spell, is given by, where did this go? I'm looking up last times. The eigenvector is of the form alpha ex plus ey. So this is what we had done last time. Oop. Is everything? Yeah, everything's still okay. So this is what we had done last time. In other words, remember how we don't care about this scalar. So we can forget about the scalar, and we know that L, so N, is just the vector ay. So this is the axis of, I'm going to scroll up before I write on something, of rotation. And in particular, oh, not the axis. This is not the axis. Oh my god, vector. This is the vector. And Ln, this is the span of ex plus ey. This is the axis of rotation. Oh my god, of rotation. Right? Now remember one thing, the trace does not change by linear operators. So the trace of p, so what is the trace of p here? It's 0, 0, minus 1. This is equal to minus 1. But we saw from previously that this is also equal to 1 plus 2 cosine of phi. So what these two things tell us is that minus 1 is equal to 1 plus 2 cosine of phi. That was a horrible O. So I can move this minus 1 to the other side. 2 cosine of phi. Minus 1 is cosine of phi. What does this give me? This tells me that phi, there. Phi is equal to pi. Now pi, it doesn't matter if I went this way or this way, pi is the same. So the angle of rotation is pi. I don't care which direction I went. And there we go. So this is a nice long example. We will stop here. And in the next video, we'll start looking at the proof of Euler's rotation theorem. And we'll start getting into the nitty-gritty of all that. So I will see you in the next video. Peace.